Okay, welcome once again in this 10th lecture on metric spaces. And as we have seen in the previous talk, the definition of a closed set, the closure of a set, interior of a set, open set, and their properties. And we have seen that a set, a subset of a metric space X is closed if and only if its complement is open. Okay, and we have also seen that the interior of a set, the open sphere is an open set, and today we will see that the closed sphere is a closed set in a metric space. So our first theorem is that in a metric space X, every closed sphere is a closed set. So let us take SRX be a closed sphere in X. So as you know that we denote the closed sphere by this notation, and we will have to prove that this set is a this closed sphere is a closed set. It means that the complement of this is open. Okay, so it is sufficient to prove to show that the complement of this set okay is open. Okay, to prove that the complement of this is open, it means that every point of this complement is the center of some open sphere contained in it. So let us take y is an element of the complement of the closed sphere. Okay, be arbitrary, and then of course because y is in the complement of the closed sphere, and so y cannot be in the closed sphere, and therefore the distance between x and y must be strictly greater than r. Okay, so here you can see that so suppose this is my open closed sphere. This is closed sphere with center at x and radius r. And now we are considering a point y, okay, outside the closed interval. Okay, so considering outside the closed interval, this one, and then we can see that here is this is the point y. Then the y is, so then this distance, okay, this distance must be greater than r, because this dxy must be greater than r. Now let us take dxy. So this is our dxy, and this is minus this is minus this is r. So this from here to here we can choose as r1. So dxy minus r is equal to r1. So we can set r1 is equal to dxy minus r. So okay, and of course must be greater than 0. Okay, and then we can form, and with this r1 we can form a open sphere. So we can form an open sphere with center at y and radius r, and we will show that it contains this y is the center of the open sphere with this is the center of open sphere with radius r1 contained in the complement of this closed sphere. So that we can prove that so we have constructed, and then let us take z is the point in this open sphere. Then dzy, because dzy must be less than r, and by the triangular inequality we have dxy is less than or equal to dxz plus dzy. And in other words, so you take this dxz is greater than or equal to dxy minus dzy. Okay, but dxy minus dzy is what? Dzy, though this is equal to, this is greater than dxy minus r1, but dxy minus r1 is equal to your r. So this is greater than r. It means that z does not lie in this this closed sphere, and hence z must be an element of the complement of this one. So a complement of this one. It means that the open sphere, this open sphere this open sphere with center at y and radius r1 lies in the complement of this one. So this is okay. So what we have taken, we have chosen this y is in the complement of closed sphere, okay, and y was arbitrary. So it means that y is the center of some open sphere contained in the complement of closed sphere. It means that this is your open set. This is your open set, and we have proved that the complement of open set is a closed set, and therefore this ball is a closed set. Now, in a metric space, always we can say that an open sphere is a subset of closed sphere. Okay, and of course, if this is a subset of this one, then we have seen that the closure of, if A is a subset of B, then the closure of A is a subset of closure of B. So the closure of SRX is a subset of the closure of the closed ball. But the closure of closed ball is equal to, because the closed ball is closed, so it must be equal to itself. So this is equal to this one. So the closure of open set, closure of open ball is a subset of the closed ball. It is not equal to. Okay, from here you can see that the closure of open ball is a subset of the closed set, of the closed ball. But it is not equal. So the closure of this is not equal to this. For example, if R is a discrete metric space, then we can see that the open ball with center at 0 and radius 1 is equal to set of all points x such that d0x is less than 1, and which is this set must be equal to 0. Okay, this will be only the center. So you will get only the which is open as well as closed in x. And while the closed ball here is this is here is less than or equal to 1. So this is the whole space. So the closed ball is equal to the whole space. Okay, and the open ball is equal to 0, and this set is closed. So the closure of A is equal to 0, and this set is the whole space R. So the closure of the ball with center at 0 and radius 1, okay, is not equal to the closed ball with center 0 and radius 1 in the discrete metric space. So in general, you cannot say that the closure of an open ball is equal to the closed ball. Okay. Now, by using, as we have proved that arbitrary union of open set is open and finite intersection of open set is open. And by using the De Morgan law, which you have studied in your class 10 or 9th or 11, so here is the De Morgan law. So by using this De Morgan law, we can prove that, we can say that in a metric space, the arbitrary intersection of closed sets in X is closed, and the finite union of closed sets in X is closed. Again, the arbitrary here we are taking finite union, okay, but the arbitrary union of closed sets need not be closed. You can consider an example for you take this is the family of closed sets in the usual metric space, okay, the closed interval 1 over n comma 2. Okay, so this is the family of closed sets in the usual metric space R. And let us take the union of this one. So if we take the union of this one, we will get this will tends to infinity. So we will get 0 open interval to 2 closed interval, and which is not closed in R. So it shows that the arbitrary union of closed sets need not be closed. However, the finite union of closed sets is closed and arbitrary intersection of closed sets is closed. Okay. Now, as we have proved in the case of open set, that is to say, the interior of A is the largest open subset of A. The interior of A, we have proved the interior of A is the largest open subset of A. Now, we will prove that in a metric space, the closure of a set is the smallest closed subset of the metric space X containing A. Okay, so this is the main thing. So the result says that, so here is we have the result which says that let XD be a metric space, okay, and A be a subset of X, then the closure of A is the smallest closed subset of X containing A. Okay, now first again here are two things. One, we will have to prove that the closure of A is a closed set, and then we will have to prove that closure of A is the smallest closed set containing A. Okay, so first we have to prove that. So first we first prove that the closure of A is closed. So closure of A is closed means if you take X is any limit, to prove that this is a closed set, okay, we have to prove that every limit point of this set, okay, lies in this set. Every limit point of this set lies in this set. So let X be a limit point of closure of A. Okay, then for every epsilon, because X is a limit point of this set, keep in mind. Okay, so for a moment you can consider this is your for example, you can consider this is B. So here you can take for a moment this is your B. Okay, so for your understanding, this I can write it is equal to B. Okay, so I just denote closure of A is equal to B. So let X be a limit point of B. X be a limit point of E, then for every epsilon positive, the open ball with center at X and radius epsilon by 2 contains a point of B other than X. That is to say, this intersection is non-empty. This implies that Y, okay, so this implies that there exists some Y in this B such that Y lies in this set, okay, is this one. That is to say, the distance between X and Y is less than epsilon by 2, okay. But since Y is in B, okay, and B is what? B is the closure of A. B is equal to closure of A. So this is, it means that it is the limit point of this set, and therefore an open ball with center at Y intersection A must be non-empty. So this is non-empty. It means that there exists a point A, there exists a point Z in A such that it also lies in this set. Okay, so Z is lies in this one. It means what? It means that dZy is less than epsilon by 2. And now by using the triangle inequality, we can say that dxz is less than or equal to dxy plus dyz, and this is less than epsilon by 2, this is less than epsilon by 2, so the whole thing is less than epsilon by 2. It means what? It means that Z is an element of the open sphere with center at X and radius epsilon. So Z lies in this open sphere. This means that for every epsilon positive, the open sphere this contains a point z of A, okay, and hence x is the limit point of A. So x is the limit point of A, and therefore x is in closure of A or in B, and this proves that the closure of A or B is a closed set. Now the second is we have to prove that we have to prove that it is the smallest open set. A closure of A is the smallest set containing A. Okay, so suppose that B is any closed set of X such that A contained in B. Okay, so suppose that B is any closed set which contains A. Okay, it is sufficient to show that the closure of A is a subset of B. So let us take X is an element of closure of A. So closure of A, then either X is in A or X is the limit point of A. If X is in A, then X is in B, and hence a closure of A is a subset of B. So if X is the limit point of A, then for every epsilon positive, the open ball with center X and radius R minus X intersection A is non-empty, because X is the limit point of A. So we have this definition, and it means that there exists a point y in A such that y lies in this set. So y lies in this set. It means that y is not equal to x, but the distance between x and y is less than epsilon. So distance is in. But since A is a subset of y and A is a subset of B and y is in A, we have y is in B, and therefore the infimum, therefore the distance from x to B is equal to the infimum over y is in B dxy, and we have proved that if y is closed, okay, if y is closed, then the distance from the point x to the set B is equal to 0. So this is equal to 0. Okay, it means y. Okay, so from here, because the infimum is equal to this is 0, so from this which we have proved that x lies in the closure of B. So x lies in the, but x is your closed set, so x lies in B. Okay, so x lies in B, hence the closure of A is a subset of B. So this way we can prove that the closure of a set is the smallest closed subset contains that set. Now we have some other definition. So we have defined other things, the limit point or interior point and the limit point. What about the boundary point? The boundary point, if we have, so now we define the boundary point of a set. So let A be a subset of a metric space X. Then a point X in X is called a boundary point of A if it is neither an interior point of A nor the interior point of the complement of A. Okay, in other words, X is a boundary point of A if every open sphere centered on X intersects both A and complement of A. Okay, for example, suppose you have this is your set X. Okay, here you have a set A. Now you take suppose this is the point X. You take any open sphere So you see, this is your open sphere SRX. So every open sphere, keep in mind every open sphere, okay, so you take every open sphere, this one or any one, okay, that intersects with A as well as the complement of A, then this point is called a boundary point, okay. So there are two things. One is we can say that a point x in X is a boundary point of a set A if it is not an interior point of A as well as it is not an interior point of complement of A. Okay. In other words, we can say that a point of X is a boundary point of A if every open sphere centered on X intersects both A and complement of A. So these two definitions are equivalent, and the set of all boundary points of A is called boundary of A, and it is denoted by BA. BA means set of all boundary point of A. Now we can easily see that the boundary of A is equal to the closure of A, okay, intersection the closure of complement of A. Closure of A intersection closure of complement of A. So that is a very important thing. So that is the boundary of A. So you can also mention from here you can get from this line you can get this thing. Now an example we have, we say that if X is the usual metric space, okay, X is equal to R is the usual metric space and A is the subset of X. If A is closed interval AB, closed open interval AB, open closed interval AB or open interval AB, then the boundary of A is the set consisting only the endpoints AB. Similarly, if A is the set of natural numbers, then the boundary of A is the set of natural numbers. If A is the set of integers, then the boundary of A is the set of integers. If the set A consisting 1, 1 over 2, 1 over 3 and so on, then the boundary of A is the set consisting 0, 1, 1 over 2, 1 over 3 and so on. If the set A is a set of all rational numbers, then the boundary of A is the whole real line. If the set of all irrational numbers, even then the boundary of A is the set of all real numbers, that is equal to boundary of A is equal to R. Now here we have an example. You can see, you can visualize it. Suppose we are considering X is equal to R2 with the usual metric. Okay, keep in mind we are considering R2 with the usual metric space. So R2 with the usual metric space and A is the open disk. A is the open disk. Okay, only this one. Okay, the cross one, not the blue one. Only this this one inside. Okay, this is the set A. And then what would be the boundary of this set? So boundary of this set would be this below blue line. Okay, the boundary, this is the boundary. Now, as every open sphere centered at X intersects both A. How it is? Suppose if you take a point X over here, okay, which is not a point of A. Keep in mind this X is not a point of A, because A is consisting all the point here, not on the blue line, okay, because this is strictly less than 1. So this is less than, and so if I take here is the point is X, a point on the bound on here on the blue line, then you will see that you take every open sphere, okay, whatever is your R. So this is your open sphere, okay, this is your open sphere which intersects with A and the complement of A. This part is the complement of A. So intersects with A and complement. Similarly, you can prove that all the point on this blue line are the boundary point of A, and therefore the boundary of this set is the blue line, this one. So the boundary of this is the blue line of this one. Now again, for your curiosity, you can see that as I have also mentioned that whenever we consider examples, we start from the real line with the usual metric, and sometimes we will try to do some other matrices on the real line, or we always check whether the discrete metric satisfy the property or not. So if X is your discrete metric space and A is a subset of X, then the boundary of A is empty. In other words, you can say that the boundary of any set in a discrete metric space is empty. Okay? Now there are several exercises that you can do by yourself. The first one, verify that every subset of the discrete metric space is closed. Okay, and prove that every singleton set and every finite set in a metric space are closed. And if let A be a subset of a metric space S, then prove that the closure of A is the intersection of all closed subsets of X containing X. And sometimes you can use this as a definition of the closure of A. So the closure of A is the intersection of all closed sets containing A. And several places it is mentioned as a definition of the closure of A. And this you can prove very easily. So here I provided some hint that suppose D is equal to the intersection of all sets B, okay, such that B is closed and contains A. Then clearly, because the B is closed and we have proved that the arbitrary intersection of closed set is closed, so we have proved that D is the smallest closed set containing A. Okay, and from the proof of this theorem we can say that the closure of A is equal to D. So here is the hint, and you can complete the proof. Now here is determine the drive set of the following set. So here you have a finite set. Okay, so what would be the drive set of this set? You can do it. If X R is equal to this, what is the drive set of this one? And if A is a subset of a metric space, then prove that the closure of complement of A is equal to the closure of complement of A is equal to the complement of interior of A, and the interior of complement of A is equal to the complement of closure of A. So this you can prove very easily. And you can also prove that if A is closed set, then prove that X is in A if and only if dXA is equal to 0. Okay, this we have already proved that X is in the closure of X is in closure of A. Okay, if and only if the distance from X to A is equal to 0. This we have already proved. But if A is closed, so you can remove by this closed set, you will get the answer here. And from here you can say that X is in the complement of A. X is in the complement of A if and only if the distance from X to A must be greater than 0. So from here you can conclude this, and this is your you have to prove this by yourself. Now here is, let us consider the set of rational numbers Q with the usual matrix this, okay, and give an example of a non-empty closed subset A of Q and rational numbers and rational number x which is not in A such that there is no y in which dxy is equal to rho xy. Recall that rho xy is equal to this thing. Okay, this you can take, here I have given provided the answer. So you can take x is equal to 2 and A is the set of all points rational numbers whose square is less than 2. And then A can also be written as this one because there is no rational number, okay, with p square is equal to 2. It can be described in this way or in this way. And then A is both open as well as closed. You have to verify it. However, the distance from 2 to A is equal to this distance, while the distance from A to P is greater than or equal to this. So here is the proof is given. There are several others exercises that you can do by yourself. Okay, so a large number of exercises are here. Okay, so I will do some exercises in my next talk. Okay, meanwhile you can try to find out the solution of these exercises, and now I am stopping over here. Thank you very much.